Okay, today we are starting with Ohm's law. Ohm's law states that, for example, there is a resistor which is connected with a battery source with a switch also, which is connected. There is ammeter in the pathway and it is connected across this way, and voltmeter is attached across the battery. There is voltmeter, and this is resistor, this is battery as EMF, and this is switch, this is ammeter. When I say voltage applied across the ends of a resistor or a conductor, voltage applied across the ends of a conductor or resistor, ends of a conductor or resistor where I have fixed the voltmeter is directly proportional to the current flowing through the resistor, through the resistor. At constant temperature and pressure. Temperature and pressure. After that, if I show mathematical expression for this one, we can simply say here V is directly proportional to I. For removing this proportional sign, we introduce a constant V is equal to IR, where R is called a resistance of that conductor, resistance of that component, which is connected in the circuit over there. R is resistance measured in ohms, and ohm is having this symbol of omega over there. And if we plot a graph between voltage and current, we will say here that let's suppose we are plotting a graph between voltage and current. Then we can say if voltage is along x-axis and current is here, then the graph will be showing it's bending towards voltage little bit. But if I change the axis, I plot current downward and voltage upward in this way, it will be more high value, but bending to be shown towards the voltage, not towards the current. So whenever we say there are ohmic conductors, when temperature is remaining constant, the VI graph line stays the straight, or we can say the VI graph line is straight, showing the positive gradient over there and remaining constant over there, and it passes through origin. Straight line is straight is also passing through origin over there. And the ratio of V over I, if I take the formula over there also, then ratio is given V over I as the resistance of this. But if you take the gradient of IV graph in this one, in this case, then I will say it will be taken as gradient will be taken, and it will give you change in I over change in voltage. Then you will have to take the reciprocal, like 1 over R will equal to delta I over delta V. And for getting the resistance, you will reciprocal it. But in this case, you will get R is equal to delta V over delta I, and you will get the resistance directly from this graph by getting the gradient. If the component, if the electrical wire or electrical component is not following your straight line, then we can say that will be taken as a non-ohmic device. Non-ohmic devices or components of the circuit are those whose IV graphs are not straight line. And for that case, we can take filament lamp. Filament lamp. For example, here I am filament lamp is that yellow color light lamp which is having a tungsten wire, which is having a tungsten wire, which increases its temperature with the passage of time over there. If I plot the graph between V and I for a tungsten wire, V along y-axis and I along x-axis over there, then I will say here it is showing a bending towards voltage over there. Or I say here I am taking the graph between I and V over there, then again it is showing the bending towards voltage over there, that this graph should be plotted like this. So at higher voltage, the current will be higher and the filament heats up and hence resistance increases. So we will also say here as the temperature of the tungsten wire increases, resistance will also increase, and your constant resistance is not going to be shown in the form of a straight line graph. Another example for non-ohmic devices, which we will mostly have to take into consideration over there, that is named as thermistor. Thermistor is negative temperature coefficient resistor, which is heat sensitive, and we can say when temperature increases, resistance decreases. This means that temperature and resistance are inversely proportional to each other in the case of thermistors. And if we plot a graph between IV graphs over there, this is I, this is V, and I in this case, then the graph will be shown like in this format, like bending towards current. And if I say I'm taking a VI graph over there, V and I graph over there, then the bending again will be shown towards current over there, current axis over there. So you will say, and for the same voltage, there is more increase in current when the temperature increases, the resistance decreases over there, and it is showing the more increase, and the ratio decreases with increase in voltage, and temperature is direct inversely proportional to resistance in case of thermistor over there. This was the second form. Third form is coming as non-ohmic device is LDR, light dependent resistor, mostly used in street lights. In this case, resistance is also inversely proportional to light intensity. In case of light intensity, we can say in the dark, when there is no light, like dark at night over there, what will happen? Resistance is high. And in the bright day, the resistance is very low, which is showing with the help of, we can say, LDR, the phenomenon over there. After that, the last one, which I will say here, is related to diode. Diode is basically a device, a component which allows the current in only one direction. Like this is positive, this is negative terminal of diode. If I connect it with a battery, positive with positive and negative with the negative using a switch also, which is connected in this format, then I will say current will flow from positive terminal to negative terminal over there. But if I take the opposite signs, like positive is connected with negative and positive is connected with negative through the switch over there, current will not flow. In this case, current will not flow. And if you introduce a small bulb over there in this form, it will lit up, current is flowing through it. But if you introduce a bulb over here also, what will
सर
happen?
मेरा एक
It will
क्वेश्चन
lit
है.
off. Yes?
I have a question.
Yes, what do you want to ask?
सर एलडीआर जो लाइक डिपेंडेंट रेजिस्टर्स होते हैं,
Yes.
इन पे जितनी ज्यादा लाइट डालेंगे ये उतनी उनकी रेजिस्टिविटी हाई होगी.
As much the light is high, resistance is low. Resistance is low, voltage
अच्छा.
drop across that resistance is low, and your street light will remain off at daytime. When at night
ओके.
time
ठीक है.
there is no light, resistance is high, voltage drop across the resistor is high, means consumption of the voltage at night time is high in the form of energy, and the street light is turning on in that case.
ठीक होगा.
Okay.
ओके. जी सर.
Okay, we were discussing this, that the diode is allowing the direction only in this, that positive is going towards the negative and circuit is getting complete. This is called forward biased for diode, and this is called a reverse bias. Like negative is connected with positive terminal of diode and negative is connected with the positive terminal of the battery over there. Then we can say it is a reverse biased. And if it is reverse bias, then I can say here that no bulb is getting on and it is remaining off over there. And in this case, bulb is going to lit off and it is on in that case. And diode is allowing the current in only one direction, in only one direction. These were the little bit examples of non-ohmic devices which are not going to show the straight line graph and showing some curves when we plot the graphs in the form of IV graphs over there. After that, we will have to move towards the DC circuits, in which we will say the resistor in series and resistors in parallel over there will be taken into account. Let's suppose I am starting the resistors in series. The resistors connected in series. For example, I'm taking here three main resistors, 1, 2, and 3 resistors end to end connected over there. There is a battery which is showing its positive and negative terminals. There is a switch shown over there, and also an ammeter showing the current flowing through it. And if the current I am taking in series case, I'm showing here 3 resistors, which S, battery, EMF, voltage, and ammeter. And if I want to calculate the voltage across R1, I will introduce V1 in that case. I will introduce V2 over there. I will introduce V3 over there in the form of voltmeter to get all the voltages over there. In series, there are two main characteristics. Current stays same over there and voltage divides. By using these two basic principles of series resistors over there, then we can say, as I said, voltage divides. Then it means the EMF voltage, which is V, will equal to V1 plus V2 plus V3. And according to Ohm's law, we know that V is equal to IR. In that case, I will say here that V is equal to IR which is equal to IR1 plus IR2 plus IR3 over there. And in that case, V1, V2, V3 is the completely divided and current remaining the same. I1 is equal to I2 is equal to I3 over there. Then in that case, by taking I as common over there, then R is equal to I into R1 plus R2 plus R3 should be taken into account. From the both sides, I is cancelled
सर
with
ये
I and I am getting
सर ये रेजिस्टिविटी इन सीरीज है ना?
yes, this is the series combination of the resistors. All right.
एंड वो दूसरा जो पैरेलल होता है वो आई ओवर आर वन प्लस आई ओवर आर टू हो जाता है.
1 over R1, 1 over R2, 1 over
सॉरी
R3,
वन ओवर.
and by taking
हाँ जी.
the values. I'm going towards that one. Don't worry. Okay, now we are going towards resistors in parallel. If we look towards resistors in, and remember that this derivation you will have to keep in mind. Sometimes he can ask you for 2 marks over there. 2 marks or 3 marks that derive this formula are like that. Mostly in papers, it is asked over there. For parallel one, there are 3 main resistors again I am taking, which are connected with a same junction over there. Let's suppose this wire, and this wire are collectively connected with the junction wire over there. On the other side, they are also connected with a simple one junction, and this is called parallel combination. And EMF is given over here. There is a switch over there. And if I study about these parallel combinations, then I will say here that these parallel combinations should be taken in this format, that the current is coming from positive terminal and current while reaching here is I only. This I is being divided into I1, I2, and I3, depending upon what is the resistance over there, R1, R2, R3. As the current is divided, so I will say here ammeter 1, ammeter 2, and ammeter 3 should be introduced. And V is EMF over there. And in parallel, all the voltages stays same. Let's suppose it is parallel combination of resistors, parallel combination of resistors I am talking about. In parallel, what I said, current divides and voltage stays the same over there. In that case, we can say here that V is divided into V1 plus V2 plus V3, while not V. V is staying the same over there. So I will write it V is equal to V1 is equal to V2 is equal to V3, and current is dividing. I is equal to I1 plus I2 plus I3 over there. In this case, for the derivation of parallel resistors formula, I will use again the formula of V is equal to IR, which tells me I is equal to V over R. So I am taking here V over R is equal to V over R1 plus V over R2 plus V over R3 over there. And if I go towards it, then I will say here how it is going on, that V over R is equal to V common 1 over R1 plus 1 over R2 plus 1 over R3 can be taken into account, and V is cancelled, and this R I am getting in the form of total. 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And remember that when you are going to get the total resistance over there, then after taking LCM and making them one unit in the form of fraction, you will have to take reciprocal of this resistance. to get the total resistance over there. This is the parallel combination of the resistors to be connected over there. And in case of parallel, with the things we will have to keep in mind that the current staying the same over there, current is dividing and voltage staying the same over there. After that, we will have to move towards power and electrical energy. Electrical power and electrical energy. For both of these cases, as we have studied in dynamics, that power is equal to work over time. I can say here work is W, over time is T. And if I just multiply here with the Q and multiply here with the Q, what I am trying to make over there, I am trying to make W over Q multiply Q over T. I have just introduced Q like chain formula in mathematics differentiation over there. Work done per unit charge is called voltage and the rate of flow of charge is called current. So my electrical power is going to become voltage into current is my electrical power formula. If I introduce according to V is equal to IR, what I am saying here, I am replacing this V with IR, then the power formula can also be written as P is equal to IR into I have just replaced this voltage value with IR, then it is giving me formula that power is equal to I square R. This is the second formula of power. Depending upon the given data, I can manipulate and use them for the calculation purposes. If I am going to replace this I is equal to V over R, as we have taken here I is equal to V over R. Now I am saying power is equal to V into V over R, then I will say my power is equal to V square over R in case of electrical power can be taken into account. After power formula calculation, we can also say how we get energy. If I look the basic formula of dynamics, power is equal to work over time. I can say work is energy, work is the form of energy over there. Power should be multiplied with time. So for energy, I will say here that energy is equal to power multiplied time, and power is VI, that is according to our formula number 1 over there. VI T is for energy to be used over there. And for getting its unit in the form of electrical energy, we can say it from the power, it is watt. For time mostly taken in electrical energy form, it is taken as 1 kilowatt hour, which we say in joules can be calculated 1 multiplied 10 raised to power 3 for kilo. Watt is just like a unit, and time joule second is becoming a joule per second, and hour per second will give me only joule form energy. Multiply 3600 seconds in 1 hour, then I will say it is making 3.6 multiplied 10 raised to power 6, which can be written as 3.6 megajoule energy is present in 1 kilowatt hour energy of electrical power unit over there. If I talk according to the formulas of power, I will say here we have seen that P is equal to I square R. Then here I can say if current is constant, then power is directly proportional to resistance. And if I take the formula number, it was my formula number 2 over there, which I have used and tried to explain that power is directly proportional to resistance while keeping current constant. So larger resistance will have more power dissipation in series over there. So this is in series. While in parallel case, then I will say P is equal to V square over R, where the voltage remains constant over there, then I can say if voltage is constant in parallel circuits, then power is inversely proportional to resistance over there. For the both cases, this I said series, where we know current remains the constant, then power is directly proportional to resistance. And in parallel, we know that voltage stays same in case of parallel cases, then power is inversely proportional to a resistance of those circuits over there. Remember that when we are taking potential differences and finding and applying on different scenarios of calculating resistances and voltages, we will have to take into account the EMFs, and we will be going with the salt bridge phenomenon over there for the calculation of different circuits calculation being taken into account. As I said here, that there is a battery which is available, and we want to take that battery in the form of EMF. Let's suppose I say here that there is a battery. Definitely, it will have little bit internal resistance also. It will have little resistance as internal resistance of the battery. I say this is whole is the battery over there. I connect it with a resistor over there. Let's suppose I say this is my main circuit resistor connected with a switch which is closed and having some ammeter over there, and this is connected here. Then in this case, I will say here that when I am taking ideal battery, even though that is not available on surface of Earth, we can say which have internal resistance small r equal to 0. That is not in a real applicable over there, but practical battery, we can say that is a battery which is having some internal resistance, internal resistance. When it is going to provide my potential difference across the main resistance R, then it will be taken as potential difference V. And in this case, I am taking EMF, electromotive force, which is provided. And the potential difference is terminal potential difference is the same as EMF in case of ideal battery, which is not in real possible. But in some cases, if he has mentioned, then you will use this. And when we are saying there is like EMF is the chemical energy, when I am saying that it is a battery, it is EMF, then we can say what is EMF? EMF is the chemical energy converted into chemical energy converted into electrical energy. When we are taking chemical energy into electrical energy, or we can say on the other end, for the same electrical energy is lost as heat on internal resistance. Like if this EMF is having some internal resistance small r, then we can say some energy is consumed by the battery itself. Then the potential difference applied across this main resistance will be smaller than the total EMF rated on the surface of we can say as calibrated or rated on the outer shell of the battery over there mentioned by the manufacturing company over there. And when I say that I want to take the voltmeter here for getting my potential difference along this resistor, then I will say terminal potential difference is always less than EMF of the source, and some of the voltage is lost during when the current is flowing across this small resistor R over there. Then I will say that the EMF is equal to voltage drop across main resistor plus voltage drop across the internal resistance over there. So for getting the value of potential difference, I will say subtract EMF with potential drop across its internal resistor over there. So this is the way how to calculate the potential difference by using the EMF value. This is very important formula which will be used in paper 2 variant 2 over there as the structured questions. Mostly it will be taken according to the definition of EMF over there. So E is EMF and small r is showing here the internal resistance, I is the current flowing through it, and V is the potential difference or a potential drop, voltage drop across the circuit of potential difference over there. And after that, I will say here, if your internal resistance, like battery is getting heat up, and I am saying here that the small r resistance of the resistance of the external circuit, when this resistance is going to increase, then definitely I will say here much more voltage drop of EMF is being consumed by battery internal resistance over there, and outside the battery your potential terminal means EMF is much being consumed, and potential difference will be provided in less quantity to the circuit as external circuit over there, and current in the external circuit are going to be taken into account. This was the potential difference which is decreasing, and the current which is provided to the external circuit over there, this increases. Remember the two effects. If internal resistance is increasing, and if internal resistance is increasing over there, EMF is decreasing, and voltage EMF remaining constant over there. This is the constant, like the battery is having so voltage, even though that is much consumed by internal resistance. After that, there is a potential drop, and there is current, which is going to increase when your resistance of the circuit is taking its value in the form of 0 over there. And if we say when the resistance of the external circuit outside the battery is 0, if I say R is equal to 0, when I will say when switch is open, switch is not closed, switch is open, then we can say that all the voltage drops, all the terminal potential differences is equal to 0, all to all, and all voltage is lost on internal only the small resistance R is consuming only for the battery inside over there, and current in the battery will be maximum, and current in the battery will be maximum that case. After that, he is going to take that how maximum power theorem can be taken while using this EMF. When I am saying that external resistance is 0 or some internal resistance is going to participate over there, then how maximum power transfer theorem works. Power transfer theorem works. For that law, for that proper rule, we know that output power of external circuit can be taken according to its formula. Power is equal to I square R according to electrical power formula. But I am saying if I replace this uh, for making the current to be taken, if I take V voltage, and now I want to replace this current with some values depending upon the internal resistance and external resistance also, then I will say here that the voltage drop across the internal resistance will be being taken as small r, that will be I small r, and voltage drop across the main resistor over there, I say that is IR. Then if I take EMF is equal to voltage across main resistor minus voltage across internal resistance, then I will say here that it should be added. It should be added. Then I will say here that it is I into small r. No, it is main resistor plus IR. If I take I as common, then it will be R plus R being taken and E is coming here. then my current is getting the value of E over R plus R. And here I am saying that I am replacing this I over here. Power is equal to E over R plus R whole square with capital R as the power resistance over there. Then we can say from here that you can take the formula power is equal to uh, E square R over R plus R over there. And if I want to take my power as a maximum value, then I will put my internal resistance equal to capital R over there. When I am saying capital
Mm-hmm.
R is equal to small r, it means it is also having the square over there. If we place this internal resistance equal to the external resistance over there, then we can say here that this whole power is becoming power is equal to E square R over R plus R whole square is going to make E square R over 2R into R squares. Then we can send take E square R over 4R square. 1R is cancelled and we are getting the value E square over 4R. And this value of expression is used for maximum power which a battery can provide into the circuit over there. And maximum power is drawn out. Maximum power is drawn out of a battery when we can say external resistance is equal to internal resistance over there. Then we can say the maximum power of the battery can be achieved over there. And if we try to plot a graph, like I am saying here, let's suppose we are taking a power graph over there. Let's suppose we are saying if we plot a graph between the power and resistance of load, power and resistance of load, then I am saying here, let's suppose the graph is shown like this, where it will have the maximum power over there. Then this is the point where external resistance and internal resistance are becoming equal over there. If external resistance is greater than internal resistance, in that case, I will say here that the low current in the circuit, so less power output, less power output will be available in this case if I provide R is less than internal resistance. Then in this case, I will say here that more heat loss on internal because the internal resistance is high. Then we can say here that more heat will be lost, more heat, more heat loss on the internal battery or internal resistance on internal resistance because it is larger internal resistance, and there will be we can say less power, so less power output is going to form in both cases over there, less output power. In both cases, the power is less, even though your external resistance is smaller than internal resistance, or external resistance is greater than internal resistance of the battery over there. In both cases, the power output will be less. And if you equate both of them, then you can say the maximum power can be attained over there. For manipulating both of these formulas in this case, as I have said, power is equal to E square R over R plus small r whole square. If I try to discuss the case, for example, I say R is equal to 0. Then in that case, what will be the power over there? Then if R is equal to 0, then I will say it will become power is equal to E square R over R plus 0 square R square. Only R is here with one power gone. Then we can say it is E square over R is present in that case. So this is the power which is available in the case of that power. When we say the resistance is R, then the power is there. We have derived this formula also, P is equal to V square over R in the previous section over there. And if I say, if I place it equal to R resistance, we have just written before, derived it, that it is equal to power maximum output is being taken E square over 4R. When we have placed small r equal to big R, like internal resistance to external resistance equal, then we say now it is equal to 4R. So I will say here P is equal to E square over 4R. This is maximum power output over there. Then if I take the maximum percentage of ideal power over there, then I can say that the power maximum is basically power ideal over 4. What is the power ideal? That is E square over R when internal resistance is 0. Then I am saying here E square over R over 4. Then it means originally it is 25%. 1 by 4 is 25% of the original power in case of ideal. That is the maximum power which even though it is low power, given longer life for a battery, we can use this maximum power over there. Now we will have to move towards Kirchhoff's laws over there. Kirchhoff's laws. Kirchhoff's laws basically relate to two main concepts behind the current, voltage, and EMFs over there. In that case, I say Kirchhoff's laws. Kirchhoff's laws states according to Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law is called law of conservation of charge, and Kirchhoff's voltage law is called law of conservation of energy. Law of conservation of energy. And if we explain them, let's suppose this is a node in which there are three wires having current is entering, and only two wires are coming out, and the wire which are entering into the node are having the current values I1, I2, I3, here coming out I4, I5. Then I can say here I1 plus I2 plus I3 is equal to I4 plus I5, which means current entering the node is equal to the current leaving the node, in which we can say sum of all the currents is equal to 0. According to Kirchhoff's current law, I can say sum of all the currents, sum of all currents entering a node is always equal to current leaving the nodes. Over there. So sum of all the currents entering a node is always equal to sum of all the currents leaving the node, and we can say here sum of current in is equal to sum of current out is being taken according to Kirchhoff's current law over there. So it is related to the law of conservation of charge, and it is applied on these type of nodes or junctions over there. And when I take Kirchhoff's voltage law, about which I said law of conservation of energy over there, then I can say sum of all EMFs is always equal to sum of all potential differences. Sum of all potential differences in a closed loop of a circuit over there, where we can say sum of all the EMFs is always equal to sum of all potential differences. Sum of all potential differences in a loop, in a closed circuit. Closed loop like that. And I can say here, for example, you are being provided with the EMFs and resistors to have their voltages and resistances. Let's suppose we take here the two EMFs. For example, I am taking here positive, negative, positive, negative. The battery with the internal resistance, let's suppose I say it is R1 in the form of small r1, and it is E1, and I am saying it is my first battery over there. After that, I am connecting it with a resistor, and I am also introducing another battery over there, which I am saying now having again the positive terminal over there, negative, positive, negative. I am connecting it with small internal resistance to be shown over there also. What will happen? I'm joining it to the other end of the battery also. Now, as I said, it is E1, it is R1. I say here that it is the big one is my uh, R2, and here I am saying it is my R3 over there, and it is E2 or E3 over there can be taken into account. And as we know, the current flows from positive terminal to negative terminal. Then I'm showing like it is flowing in this format from positive to negative terminal of the battery. So it is positive to current which is flowing through it. If I talk here, positive terminal of the battery is connected with positive terminal of the battery. Negative terminal is connected with negative terminal of the battery. So when it is happening that positive is connected with positive and negative with negative, then we will have to take the difference of batteries. E2 minus E1 I am taking here. And sum of all EMFs is being taken equal to V1 across resistance R1 plus V2 across resistance R2 and V3 across resistance R3 over there. And I can say here E2 minus E1 will equal to I R1 plus I R2 plus I R3, let's suppose I said over there. So sum of all EMFs will equal to sum of all potential differences.
सर मैं आपकी क्लास में शुरू करूँ
Okay. This is the way how Kirchhoff's voltage law should be applied to prove that sum of all EMFs is equal to sum of all potential differences in this closed loop. Remember that I can add more loops on both sides over there where only no EMF is available. I am introducing only one resistance I am introducing another loop. Loops can be much, much greater in both of these cases, and they are taken into account. What happened? No? Where is remote? Get it. Get it. Get the remote. So this is Kirchhoff's voltage law and Kirchhoff's current law. Now we will have to move towards potentiometer. Potentiometer. Potentiometer is basically a device, a wire fixed of fixed resistance that has potential difference across its ends. Let's suppose this is the wire with its terminals A and B, and this wire has fixed resistance over there. Resistance. And what we will have to do with this wire over there for showing the potentiometer as a variable resistor over there, I am connecting it with a battery. No. Yes. Here I was saying that this is a
जी
fixed
सर.
resistor which is connected with a battery over there. Battery is available over there, and it is connected with some load resistor over there, and this is in this format. And from the terminal A, I can say here I will have from this terminal A, I will have a voltmeter connected, and there will be a sliding contact which can decrease its resistance to be taken into account to make the output power to be useful over there. I will say here this junction A is touching the point, let's suppose C over there. Then the resistance to be taken from this initial point to C over there will be taken as a small length, and AB is the total length over there. In both of these cases, what I will say here, let's suppose you are taking and measuring the voltage V across X, Y form, then I will say this voltage X, Y will be being used as, let's suppose you are saying A to C as a distance, let's suppose I say here small x, and small x over total length of AB should be multiplied with the voltage which is provided across the full AB. Voltage across AB as potential difference will give me the voltage drop across AC over there. It means the voltage or potential difference provided to the whole wire is divided into the some section over there. So potentiometer is a device which is used as potential divider over there. And this potential divider is basically used to divide the voltage according to the requirement. For example, we want to use a source like a charger from 220 to 10 volt or 7 volt for mobile phone. We can apply this, even though this is not this will not be too much comfortable for it, or LED, which is mostly available in our remote over there, and we are also manipulating that bulb for larger energy consumption device. So potential divider is available according to the requirement to provide the voltage for any appliance over there. And if a component of a voltmeter, lamp, resistor is across the component, the one junction is fixed at R like that, like resistance R as a resistor as a junction at point C. Then you are saying you are fixing this junction point over there, and voltage across the component will equal to voltage across the length X as a wire, which I have taken to show the complete detail of potentiometer. If the voltmeter was replaced by a lamp, then the brightness of the lamp can be controlled by using potentiometer circuit. If I replace it, then I will get the values of current to be taken into account in case of potentiometer. After that, comparing the EMFs, finding unknown EMF, then it can also be used over there, like potentiometer case over there. It can be used for measuring unknown EMF. For example, I am providing you here an EMF with some resistance R over there, and I connect it with I connected this terminal with a wire over there, and this wire is having this point, this wire is having this point, and I have here a meter rule fixed over it, which is having a calibrations over its surface. And this whole wire length is being taken into account from point A to point B over there. This is point A, this is point B over there. And you are providing it with for EMFs. What you will be going to do for EMFs, you are providing the EMF of a cell which is unknown. And let's suppose I say this original one is E1, and this which I want to know what is the voltage of this EMF. Let's suppose I say it is E2. I am providing here a galvanometer, which can be shown with the symbol of arrowhead into the circle over there. And I am providing a sliding contact over this wire with the help of galvanometer. When it is showing the deflection, then it means it is connected with some external circuit, and I'm joining these points over there like this. And this is the main resistor R over there. For example, I want to divide my potential difference over there. Then I will say that the small length X, which is taken from here to here, this length, small length X over total length, let's suppose I say from here to here, like as this point, I say this is length L, X over L into the resistance of wire, into the resistance of whole wire, like I can say resistance of AB will equal to a resistance from A to C over there, or A to, let's suppose I will take this point AC, a resistance of Rx, like that. For that length, I'm saying the resistances are divided. After the resistance, we will have to, if we have to take the EMFs over there, then we take Vx will be our E2 for this EMF. Vx is a potential drop across this resistor X. So we will say it is E2. And Vx of wire will be taken as IRX over there, can be taken. So for this one, we will have the formula like Vx is equal to X over L into E2, E1, which is the original EMF, will equal to E2. So that is EMF calculation over there will be taken into account. So and for this one, we should always remember E1 should be much larger than E2. And then we can say like terminals of both EMF should be facing one another. So remember that your positive will be connected with positive. Your negative side from this side is coming and connecting it with the negative side over there. So these are the two rules where positive is connected to positive, negative is connected to negative. This is the way how to find the EMF of unknown battery source over there to be taken into account. So this was your Kirchhoff's laws, potentiometers, and potential divider for the potentiometer to be used for calculating unknown resistance and for calculating unknown EMFs of the circuit. This is your whole topic, which should be memorized and revised so that easily formula manipulation can be done.
जी
Okay.
सर, जी सर।